Impact noise in a residential apartment. Sound is transmitted in buildings via many paths, but it's easy to classify them in two ways. Firstly, the sound that reaches partition elements by propagating through the air is called airborne sound. On the other hand, sound that starts as a vibration or an impact in the building structure itself is called structure-borne sound. When we look at this figure here, we can see the difference between structure-borne and airborne sound sources. So for instance, on the right-hand side here, we have a television. So sound coming out of the television is propagating through the air and then hits the floor construction, sets the floor construction into vibration, and then is re-radiated as airborne sound in the receiving space below. On the other hand, someone walking on the floor above imparts a vibration or an impact directly into the structure. That structure is then set into vibration and then radiates that impact as airborne sound into the neighbouring space below. And that is called the transmitted impact noise. Just to summarise some standards and design criteria we use to control impact noise, the Australian Green Star system or Green Building Rating System stipulates impact noise standards that have to be met in residential buildings. It is measured in terms of the weighted impact sound pressure level in a neighbouring space or in a receiving space. The standard says that we must meet a weighted impact sound pressure level of 55 dB above all residential accommodation spaces and 60 in all other spaces, for example, in office spaces. So I'd like you to keep that 55 number in your mind as we go through this case study for impact noise in a residential apartment to see if we can meet this standard for Green Star. So in this case study, the apartment above was being renovated and completely gutted and fitted out again. So the apartment owner below took the opportunity to approach the owner of apartment above who was doing the renovations to request that they put some mitigation methods in place to control impact noise transmission into the apartment below. This is the view from the apartment above. So it's in a luxury part of Sydney with views over Sydney Harbour. The apartment block was built in the 1970s with very low floor-to-ceiling heights and no balconies. So one of the critical factors in determining any mitigation methods to control impact noise transmission to the apartment below was to keep the thickness of the floor build-up as thin as possible to maximise that floor-to-ceiling height. During the renovation of the apartment, we were able to produce some 1 metre by 1 metre prototypes of different floor build-ups that would be used to control impact noise to the apartment below. We were able to test this using a standard tapping machine. Here's some photographs of the apartment above and some of the samples that we used. Here's two different tiled samples which had resilient materials as underlays to the tile surface to prevent impact noise transmission. Because the apartment was under renovation, we had the opportunity to do a lot of prototype testing before the final selections of the floor surfaces were chosen. And here's a photograph of the apartment below. As you can see, there is already a plasterboard ceiling in place, which serves as an air plenum for the air conditioning system. Here's a photograph of the bedroom, again with a set plasterboard ceiling. And here's a picture of the living room. As you can see, there are blinds covering the windows here, and the plasterboard ceiling is inset to allow for the pelmet or for the blinds to roll up. This could potentially be considered an acoustic weakness. Because we do not have the suspended plasterboard ceiling, this could be considered an acoustic flanking path between the apartment above and the apartment below. So the problem, the floor-to-floor ceiling height was very low because it was a 1970s era apartment block. So we had to keep any potential mitigation build-ups for the floor to be as little as possible to keep the adequate head height in the apartment above. There was no opportunity to put additional ceiling treatment in the apartment below. The owner was not interested in pulling down their existing plasterboard ceiling for further remedial treatment. So here's the solution we came up with for the tiled floor, which would be used in the kitchen and in the bathroom areas. As you can see just from looking at this detail, a lot of effort was put in to achieve the impact noise mitigation to the apartment below. It actually involves a build-up of different materials of different densities to prevent the impact noise transmission. First of all, we have the outer surface, which is the 12mm tile build-up. We then have a tile adhesive, which was specified by the specialist manufacturer we were consulting for impact noise mitigation. It then has a 12mm layer of tongue and groove plywood. It then has a 5mm resilient layer called wave bar, which is a rubber, which provides impact noise resistance. We then had a 16mm layer of plywood underneath, and then a second layer of the Regupol resilient layer. In this case, it was dimpled. So the combination of the different rubber build-ups, the different plywood build-ups, and the tile itself, separated with the adhesive, provided the necessary impact noise isolation to the apartment below. What was also important was the edge detail where the tiled floor met the walls. If we did not provide adequate impact noise resistance or resilient material there, we would have a flanking path of impact noise going down the walls of the building to the neighbouring apartment. And here's a photograph showing the overall thickness of that tile build-up. As you can see, it was about 54mm. 60mm was the maximum thickness that we were allowed to go to with this build-up, so we met that criterion for the design. And you can see the close-up picture of the tile surface, the plywood layers, the Regupol resilient layer in between, and then the dimpled Regupol resilient mat at the bottom. So the wood floor solution was similar in its build-up by the way we used different densities of hard and then resilient materials. One of the important differences here is that we had to be careful to choose screws that did not bridge the whole isolation build-up. And as you can see, we specified a screw length that did not penetrate the bottom layer of the waffled wave bar build-up. The thickness of the wood floor solution was around 53mm, as shown in this photograph here. We undertook some prototype testing of all the different tile and wood floor build-ups, and we first of all started by doing a prototype test on the bare concrete floor alone, which theoretically should give us our worst case scenario for the impact sound pressure level in the apartment below. What we used was a standard tapping machine, which consisted of a series of weighted steel hammers that randomly hit the floor surface to produce an impact sound pressure level we could measure in the apartment below. This is a close-up picture of that standard tapping machine sitting on our wood floor solution. And here's a picture of it sitting on the tiled floor solution. So here's some prototype test results. As well as us coming up with our recommendations for the tiled and wood floor solution, we were representing the owner of the apartment below. So the architect that was appointed to do the renovation for the apartment above also had their version of their build-ups of the two different floor surfaces. So it became a friendly competition between the architect and ourselves as to what would come up with the best impact noise resistance to the apartment below. So remember, we specified that the design sound pressure level for impact noise was 55 dB. That was our criterion to meet the Green Star Green Building Rating System requirement. For the bare slab, without any impact noise resistance or any build-up, so on the bare concrete slab in the kitchen, we were getting an impact sound pressure level of 72 decibels. With the architect solution, they got 55 decibels, so they met the requirement. For our solution, In the kitchen for the tiles, we got 47 dB. So we obtained an 8 dB improvement over what the architect could achieve out of their build-up. For the bedroom scenario, the bare slab gave very similar results to the kitchen with a 71 dB impact sound pressure level. In the bedroom, the architect achieved 56 with their build-up on the timber. For our timber solution, we achieve 52, so a slight improvement. In the living room, the bare slab achieved 67 dB impact sound pressure level, and the architect with their timber build-up in the living room achieved 55, while we achieved 50. What I now wanted to show you is how the impact noise spreads across the different frequency bands to give you an idea of what it might sound like in the apartment below for different build-ups. As you can see here, the impact sound pressure level drops off steeply as the frequency increases, which tells us that impact noise in residential buildings is usually of low frequency content between 100 Hz and 315 Hz. The dark blue line here shows the kitchen scenario here. So with the solid blue line, with the tile build up in the kitchen, you can see that we get a flat impact sound pressure level of around 55 up to 200 Hz, and then it drops off. The brown lines show what's happening in the living room. So with the solid brown line, you can see that with timber, we get a higher impact sound pressure level than what we're getting from the tiles. So we get more of a drumming sound from a timber build-up than what we do out of a tile build-up. The grey lines show what's happening in the bedroom with the timber build-up. It's quite similar to what is going on in the living room because they are both timber build-ups. So let's look in detail more at that low frequency component of impact sound pressure level. You can see just for the timber build-ups, the grey and the brown lines, we have an increase in impact sound pressure level over the tiled solution, as I mentioned in the previous slide. Now what I wanted to play you is what it actually sounds like with the tapping machine operating and what you would hear if you were in the receiving space below. This will let you hear the difference in what tile sounds like compared to what it sounds like with a wooden floor in the apartment below. So first of all, let me play the bare concrete floor as if you're in the apartment below, and then we'll play the tile build-up solution so you can hear the difference. So here's the bare concrete floor. Now I'll play the tile build-up solution below. So you can hear a substantial reduction in impact noise by using the tile build-up solution. Let's go into the living room and listen to the bare concrete floor first. And now we'll listen to what the timber build-up sounds like. So just to let you hear the difference between the tile and the timber, I'll play the tile first and then the timber build-up. I hope in those last two demonstrations you heard the difference between more low frequency drumming noise with the timber versus what you heard with the tile. I'll play it one more time. So I'll play the tile first. And now the more drumming noise of the timber. The final demonstration is what you hear in the bedroom. So here's the bare concrete floor. And here's the timber solution.